اعمل ريكورد علشان انزل لكم اياه بعدين على SULMS. اوكي زين. Okay. Now another problem I have here today, two problems. One on inverter, different type of inverters, and the second one on forward switch mode DC power supply. So let's start with the first one. I will read the problem and then we'll solve it together. Now the problem is talking about the ripple in the output current. You remember ripple? We talked about ripple in square pulse, square inverter, square wave inverter, and in the pulse width modulation inverter, and we discussed how ripple happen and how we integrate to find ripple in current. Now the first harmonic, okay, let me continue. Single phase full converter. When we say full converter, it means 2 legs, 4 switches. And also we're talking about the VD. Now it's not VD over 2, it's not half bridge, it's full bridge. Okay. The first harmonic of the output voltage is given by VO1. VO1 at a frequency which is 47. So this is a fundamental frequency F1. The load is given in figure. I will show you the figure in the next slide. As L inductance given, which is 100 millihenry, in series with ideal voltage source. Okay, back EMFs means look like motor. It is assumed that the converter works in square wave mode. Okay, first it will work in square wave mode. Okay, now he told me to calculate the value of VD, which gives VO1. You remember VO1, we say this in square wave, we say it is 4 over pi VD. So we can find it directly from the formula. Okay, I will show you the next slide. Then calculate the peak value of the voltage of the ripple current. Okay, we will calculate the current, the ripple in current. I'm having my tea, by the way, just having my tea. The conditions are the same as in A, okay, in the square, but the converter operates in sinusoidal pulse width modulation. Now, let's assume that our converter is not anymore square wave. It becomes pulse width modulation, bipolar modulation also. He gave you frequency modulation MF to be 21 and amplitude modulation MA to be 0.8. Let me see what he wants me to do. He told me which value of VD give VO1. Oh, just it's the only formula change. Rather than it's VO1 4 over pi VD, it will be VO1 equal to MVD, as you remember. Then he asked me to explain why the ripple current has its peak value at the zero crossing of the first harmonic voltage and find this value. By the way, I discussed this in the lecture session at that time on the figures. Okay. Then find the RMS value of the fundamental frequency voltage and some of the dominant harmonics. You remember when we discussed inverter, we solve these similar to this one, the fundamental and its sideband harmonics on half leg and full leg. And there is table we use it. You remember? Okay. Then next, he asked me the conditions are the same as in A again, but the output voltage is given by voltage cancellation. Oh, you remember voltage cancellation? We have alpha and beta. There is formula. We use it. But he told me that VD changed now to become 389. What do you want me to do? Just a minute. Calculate the overlap angle alpha and the peak value of the ripple current. Okay. Now let's take them one by one. The first one, when it is square wave, you remember square wave, very simple. VO1 equal 4 over pi VD. 4 over pi is 1.273. And I want VD, VO1 given to me. Let me find VD. Just divide directly, calculate it. Now, the peak value of the ripple to be calculated. You remember I mentioned for this, we have VL equal L DI over DT. This is from principle in level 2. And then cross multiply IL will be 1 over L integration VL DT, right? So we use this formula at that time, rather than R, it will be ripple here, ripple, and here V ripple, okay? Then it will give VD over omega L, which is XL at the end. Omega is 2 pi f. F is given to me in the question. Inductance is given me in the question. And VD I already calculated. So let's substitute to find the ripple. Ripple is 5.852 ampere. Okay. Now, the second part, he told me that use the same inverter, but now change, rather than you have square wave, use pulse width modulation, bipolar modulation. He told me that MF is 21, MA is 0.8, solve it. You remember, the formula is VO1 equal MA VD. Now let me ask you before I go further to find it. It's easy to find it, right? Just substitute, it's easy. What if I'm talking about half a bridge, one leg? What is the difference or the change will be in this formula? Anybody can help? This is a question. What should I change here in this formula for half a bridge? Anybody? Anybody?
Define.
Excellent. Divide by 2. Excellent. Divide by 2. You see, in half a bridge, we just need to divide here by 2 because it is half a bridge. Okay. So I got VD. Now he told me why. Why? Because I explained this on the figure. I don't have the figure here, but it's there in the lecture. And if you back to my record, you will find that the explanation there. But simply, you see that I ripple approaching when the maximum voltage approaching its maximum value. For that, we reach the maximum value. Also, he told me to find the ripple current. I calculated here the ripple current for square wave. Let's calculate it for pulse width modulation. Denominator is the same, 2 pi f1 by L, but the numerator changed. It is the new value of VD. I got it. You can see here ripple increase. Okay. Okay. Now, next, he told me to find the RMS fundamental frequency voltage and some of the sideband harmonics. I solved something similar to this question in the lecture session. You remember? It will be 1 over square root 2 times VD by the ratio, which is to be taken from where? From the table. We have the table. Yeah, remember the table. Now, VD, I have it. I already calculated. Where is it? This one. Okay. Now, so when I divide by square root 2, I got this value. What is left is this ratio. I need to get this ratio from where? From the table. So I go to the table. I will say that, okay, I will find, just a minute, let me get back here. How much MF? MF is 21. 21. Okay. 21. Okay. So what I will do, I will find first the fundamental. Fundamental is this value, which is here. We just calculated, as you can see, by the ratio. I go to the table, as we explained, on the column when MA is 0.8, as you can see in the question, I got this ratio. It's found to be also 0.8. I multiply it, I got the fundamental. Then I can find 2MF plus minus 1, 3M, and so on. Okay? So 42 plus minus 1 plus minus 2. Just try to find different frequencies. I got here as example 2 frequencies. From this one is the same, as you can see here. It's not changed, it's the same. But the ratio will be changed. From where I get the ratio? From the table. Okay. Now, last part is talking about voltage cancellation. He told you that we change VD now, and I want you to find the overlap angle alpha. Okay. Now, alpha related to beta, and we have formula for beta. Have a look here. Now, I have VD. I have VO1. He told me it is not changed, 220. And VD, he gave me this value. Okay. What is left? Beta. Rearrange the equation, you find sine beta. Then you do sine inverse to find beta. When I got beta, there is formula tell me that alpha is 290 minus beta. So I just need to substitute to find the beta. Also, he asked me to find the ripple involved in current. By the way, you see the ripple in current over time, we have the same denominator. The numerator is changed. VD is changed. So the ripple increase. So if I compare the three cases, I'll find that the ripple and voltage cancellation is higher than pulse width modulation, which is how much I found it, just a minute, 9 point, which is higher than the square wave inverter. This is the first problem, okay? Any question on the first problem? Any question before I move to the second one? Clear? Amal, شيخة، أصيلة، خليفة، مرطيبة؟ السؤال الأول؟ Great. Let's go to the second one. Let's go to the second one. By the way, I try to make sure that the examples here contain many information, because what happened in the real life when you work in a company or in an organization, you don't expect that they give you only the needed information. They give you a set of information. You have to know what to use, what to leave. So I try to put here many information, but part of them will be used. Okay. A push-pull converter with a center tabbed rectifier. Okay, so he told me push-pull converter. Do you remember? Transformer with center tab at the primary. We have two switches. One of them will conduct half of the time. The second, you remember this? Okay. Choosing for 12 volt to 18 volt plus minus 18, 72 watt automotive power supply. So he gave me the output and the output. You are to design transformer for this converter. Just a minute. It is not normal push-pull. No, this is with a transformer. You remember, this is a switch mode DC power supply. We have this transformer. So we're talking about maximum flux density. We have to talk about the number of turns, this stuff. Okay. Now, what he told me also, use 1 to 2 turn ratio. I mean, N1 to N2 is 1 to 2 for the transformer. For the purpose of the transformer design, you can assume all other components are ideal. And the full specifications given to you is, have a look. V input range between 10 to 15 volt and nominal, the average is 12 volt. V out is 18 volt with 2 amp and minus 18 volt DC with 2 amp. This means there is a rectifier at the output also. Okay. Frequency of operation 100 kilohertz FS. And it's the push-pull is working in continuous conduction mode. Great. He told me that the transformer operating at recommended peak flux density at 100 kilohertz, 100 millitesla. He gave me here B. Okay. Flux density, B max. And the frequency, 100 kilohertz. Okay. The transformer will be based on an ETD29 core of 3C90 ferrite material. So he told me the type of the transformer. So I need to take these codes, put them in the Google them. Then you find the data sheet, and from the data sheet you are going to use some information. Before I continue with reading the question and solve it, let me show you part of the table of the data sheet I brought it. You see here at the top, ED. You see here, ED. Okay, and this is the core. So these are the information. Based on them, I got the data sheet. I remember Umayma maybe you asked me about this, about the data sheet, how we use it, and so this is a question related to this one. Okay. MashaAllah, Umayma is excited. Okay. Now, what is the expected transformer core losses? He asked me about the core losses. If the copper losses is equal to the core losses, what percentage of the converter power rating is the overall transformer losses? Okay. So he talking about the core losses, and if the copper loss is equal to the core losses, what is represented from the percentage of the total? Because you know the total is 72 watt, the total power output. So how much this represent as a fraction? At the end, it means I will divide it by 72 multiplied by 100% to see the percentage. The second part, He asked me, what is the minimum number of primary turn required to remain under the recommended 100 kilohertz peak flux density? You remember there is formula. I talked about it last session. Delta P max equal, you remember, voltage over N1 frequency. You remember this. N1 is what I'm talking about, number of turn ratio. See, I'm still reading the question. You see it's long, but since we understand it will be easy to solve. Estimate the power dissipation in the primary winding, okay, on these two switches. Based on this, estimate the total transformer power dissipation and compare with part A. Comment on the stability of the transformer core for this power rating. Let me take them one by one. First, he asked me about the losses, core losses. I know that my transformer is having this code. I go to the internet, as I mentioned, I Google it, I got the value. Any bold value here I put bolded, it means it's taken from the data sheet. Let me check. 30C90, just a minute. Where is 30C90? This is 30C90. Okay. Oh, 0.6 watt. It means 600 milliwatt. Okay. So I got it from the table. This one, is it clear from the data sheet how I got it? I took the code for the transformer. I went to the data sheet. I already got it from Google, and then I try to find the losses. Got it? Clear? Is it clear?
Clear.
Yes, Doctor.
Great. You are following. That's great.
Yes,
That's
Doctor.
great. The copper losses, he told me if the copper loss is equal to the core losses. Since the core loss is 0.6, if the copper loss is also 0.6, 0.6 plus 0.6, how much? 1.2. Great. Now, how much this represent as a percentage? I will say, okay, 1.2 divided by 72 by 100%, it will give 1.6 altogether. So from this 72, I lose 1.6% of this 72, which is 1.2 watts. This is the first part. Question. This question, part A, is already completed. Let me remind you with part B what he asked me to do. What is the minimum number of a primary turn ratio, it means N1, to remain under the recommended 100 kilohertz peak flux density? Okay, I need D. Duty cycle is important to be found. So let me find D and then I go for this. Now D is, as you remember, this is push-pull, okay? Push-pull converter. So output, okay, equal N2 over N1, D, the input, okay? It's stepping down. So N1 to N2 is known for me. This is 2 to 1, okay? And the output is known to me. Input, then can I find it? Yes, I can find it directly. By the way, he asked me that the circuit, our converter, is ideal. So there is no forward voltage drop across the switches. It's only the output voltage, which is 18 volt. So I did the multiplication, 18 over the voltage. I took here 10 volt. Why I didn't take, as example here, 12, the average or the maximum? I took the lowest voltage. Go to the worst situation in our design. Okay. Then I got the duty cycle is 90. This is 90.9, right? This is the maximum duty cycle. By the way, this duty cycle is not for one switch. No. Each switch take half part of this. It means around 45%, 0.45. 0.45 for switch 1, 0.45 for switch 2. Or why don't we approximate to make it 50-50? At the end, it's meaningless to say 0.45 or 0.5. Okay? So we can assume it in this way. Just 1 second. Okay. Now, next, I will go to the formula. You remember this formula? VD equal 4 N1. N1 is what I'm looking for. Area, Fs, delta P max. Okay. Now rearrange the equation. It's become in this way. Okay. Now VD is the input voltage, which is already given. The lowest voltage is 10 volt. For is there in the formula. AC is 100. Sorry, this is the frequency. Okay, which is FC. And AC, the core, you see it's bold. It seemed to be, I got it from where? From the table. 76. Where is 76? This is A effective area is 76 millimeter square. So it's 10 to the power minus 6, as you can see here. And times delta P max. Delta P max, he told me it is 100K, 100 kilo Tesla. So it's mean 0.1. Okay, 100K mean 0.1. So when I divide, I got the number of turn. By the way, this is with the fraction, 0.29. We cannot, use with the fraction. Usually approximate to, let me say, an integer number. So either I assume it is turn ratio here, by the way, when I say 3.29, if I approximate it to 3.5, because we have at the end integer number. You remember the push-pull inverter, we have center tab at the transformer here. You got it? So this one, these terms and these terms together should be integer. So if I assume 3.5 times 2 to have here and here, it will be 7, which is integer. Okay, or I assume this 3.5 to be, or let me say this 2.29 to be 4. Then the total turn ratio will be 8, because 4 here and 4 here, 4. Okay, but when I use this 4, if I assume to be approximated to 4, okay, then I need to back to justify, or let me say, make sure what is the difference which will give me the same effect. It means I back to this formula here. Okay, I change this for N1 to be 4. Area is the same, Fs is the same, Vd is the same, but delta P max will be different. Okay, so I will not work with 100 millitesla, I will work with 82 millitesla. You make this as a concentrate for your circuit. Your transformer will work with this amount of delta P max. Next, he asked me to estimate, I think this is clear, and one, just formula, we substitute to find it. Estimate the power dissipation in the primary winding. Okay, now in the primary winding, you divide the current. You can see here, to find the current voltage over the average power over the average voltage, give me the current. It's DC, 6 ampere. Okay, and power losses in part of the winding on N1 here for switch 1 as example is I square R times D. Okay, I square R times D. Why D? Because each switch will work part of the time, which is 0.45, or let me say 0.5. I assume it is 50% of the time. Okay. Now I already calculated, which is 6. R, I need the resistance of the winding. From where I got it, you see it's bold. It seemed to be I got it from the table also. It's not given the question, but from the table you can find it. Okay. I got 25 milliwatt. But since I have 2 switches with 2 windings, then it will be 25 plus 25, it will give me 50 milliwatt. This is the total primary house. Then if I lose in the primary winding 50 milliwatt, how much I should lose in the secondary winding? Supposed to be 2 double, because the ratio N1 to N2 is 1 to 2. So I need to multiply by 2. So it will be 100. 100 milliwatt is lower than the core losses, which is 600 milliwatt, 0.6 watt. I mentioned for this. Okay, I mentioned for this in the question, which is 0.6, or let me say 600 milliwatt. Well, it's available in the data sheet. Now here as a comment, because of the losses is lower than the core, it seemed to be I use transformer with bigger needs. Bigger than the needed. Okay, can I use this as a credit for me? Yes, I can use it. Rather than you use larger transformer, use lower transformer. You may say at the end, I'm talking about something in milliwatt, fraction of watt. It's meaningless. Yes, if you talk about one circuit, but if you talk about billion circuits, used in our chargers for our laptops, for our mobile phones, for our receiver, our appliances, it will be huge and it will make difference. Besides, if you use smaller high frequency transformer, this is a credit. This is a credit because you reduce the size at the end. You reduce the size of your equipment, and this is one of the properties of the new technology. We are looking to reduce the size, reduce the weight, increase the efficiency, reduce the power losses, reduce the cost, reduce the complication, make it more simple. This is the technology, the new technology. And let me say, I finish the second problem, okay?